Hi friend, welcome all to my educational channel Math A to Z. Before taking forward step on group theory, it is better to understand and know what is composition table, or what is operation table, or what is Cayley's table. These three are same: composition table, operation table and Cayley's table. This is known as Cayley's table because the mathematician Cayley it first introduced in 1854. So it is called Cayley's table also. And this table, composition table, helps us to identify a finite set is either a group or not. Now, what is composition table? A binary operation star on a non-empty finite set, non-empty finite set can be defined by a table called composition table or operation table. So here the set G must be finite. Let it contains n element named A1, A2, A3 to An. Now we draw a composition table as this is the composition table of the finite set G with respect to the binary operation star. Here is n row and n column also, and another topmost row contains the elements A1, A2 to AJ to AN, and the top left or left column contains the element also. This is A1, A2 to AI to AN. And the northwest cell of the table contains here the binary composition star. Now we calculate all the binary composition. All the binary composition means here n cross n binary composition, and the binary composition star on A1 and A1, that is A1 star A1 here, A1 star A2 here, to A1 star AJ here, to A1 star AN here. Similarly, we fill up all the cell of the table, and here ith row and here ith column, and this cell IJ cell contains AI star AJ. Okay, this is the composition table or Cayley's table. Now we consider a particular example to better understanding of composition table. We consider the set of cube roots of unity, that is 1 omega omega square, and since this set contains only 3 elements, so the composition table contains 3 row and 3 column, and we write here the element 1 omega omega square and also in the column 1 omega omega square. And here the binary composition is usual multiplication, and we write the usual multiplication dot. Now 1.1, this is 1 right here, 1 dot omega, this is omega, 1 dot omega square, this is omega square. Similarly, omega into 1, this is equal to omega square, and this is omega cube. Omega into omega square equal to omega cube, this is equal to 1. So this is 1. Now omega square into 1, this is omega square, this is omega cube, omega square into omega, this is omega cube, that is 1, and omega square into omega square, this is omega to the power 4, this is omega cube into omega, this is 1 into omega, this is omega. So it is omega. Okay, this is the composition table of the set S, which is cube root of unity. Now we see that how to say the set S, that is the cube root of unity, with respect to the usual multiplication is a group or not. Okay. Now the first property of group is closure. Here we see that all the 9 elements, that is 1, omega square, omega square 1, omega square 1, omega. All the 9 elements of the composition table belongs to the set S. So set S together with usual multiplication must be closed. So the first property is closure, it is whole. Here we write, and the second property is associative. Here we see omega into omega square, that is omega into omega square. This gives the result 1. Okay. Now if we multiply here omega, so there is also omega, and this gives us omega, right? Now if we operate omega into omega first, then from this result we get omega into omega, this means omega square, into omega square, this is omega square into omega square, so omega to the power 4, so omega. Okay, that is, we say that omega into omega square, this is equal to omega into omega square. And similarly we see the associative block for all the elements are whole, and it is easy to see from this composition table. So the second property, that is associative property, is also whole. Now we go to the third property, that is identity. Here we see that the first row and the first column are the same. That is, here 1 omega square, here also be 1 omega square. And first column is 1 omega square. So from this row and this column, we see that this element, if we operated from the left, gives the result the same, and if this element is operated from the right, this gives the result same. So that is 1 into A equal to A, also A into 1 equal to A, for all A belongs to S. So from the first row and first column, we say that 1 is the identity. 1 is the identity. Okay, so the identity property also hold. And the last property of the group is inverse property. Here we search for the identity element in each row and each column. Okay, here in the first row, here is the identity 1. In the second row, here is the identity 1, and in the last row, here is the identity 1. And we see the top and the left, and from this we say 1 into 1 equal to 1. From that we see omega into omega square equal to 1, and from that we see omega square into omega equal to 1. Okay, and these three relation gives us that omega inverse equal to omega square. Also omega square inverse is equal to omega, because omega into omega square gives unity and omega square into omega gives unity, right? And also 1 inverse equal to 1. So 1 omega and omega square have inverse. So so the inverse property is also exist. So this forms a group under usual multiplication. Now another property can be seen here. In any matrix, this is any matrix, this is the principal diagonal and this is the off diagonal, right? If we see that the composition table is symmetric about the principal diagonal. Here the principal diagonal is this 1 omega square omega. Okay, and we see that the omega square, here also omega square. So this is symmetric, and here 1 omega. This is symmetric. Composition table is symmetric about the principal diagonal. Since composition table is symmetric about the principal diagonal, so S dot is abelian proof or commutative proof, right? So from the composition table it is clearly see that it is group, also it is a commutative group. Now we consider another example. The set of 3 symbol 1, 2, 3, this is S, and the set of all permutation of S is denoted by S3. That is, S3 contains row 0, that is 1, 2, 3, 1, 2, 3. This is also denoted by E or I. Row 1, this is 1, 2, 3, 2, 3, 1. This is in cycle 1, 2, 3. And this is in cycle 1, 3, 2. And this is in cycle 2, 3, because 1, 2 is fixed, and this is in 1, 3, and this is in 1, 2. We construct the composition table on S3 with usual composition of mapping. Here in the top row, row 0, row 1, row 2, row 3, row 4, row 5, and the left column is row 0, row 1, row 2, row 3, row 4, row 5. Now we calculate all the cell. Here, if we consider row 2 into row 3, in this cell, row 2 into row 3, okay, row 2 composition row 3, this is equal to row 2 composition row 3. Here we calculate row 2 composition row 3. This is row 2 means here we write row 2 1, 2, 3 and 3, 1, 2. This is row 2, and row 3 means 1, 2, 3, 1, 3, 2. Okay, 1, 3, 2, and we product these two elements as 1 go to 1 and 1 go to 3. That is 1 go to 3 directly. So here we write 1 to 3. Now 2, 3. 2 go to 3 and 3 go to 2. That is 2 ultimate go to 2 go to 3, 3 go to 2. That is 2 ultimate go to 2. And obviously 3 ultimate go to 1, because 3 to 2 and 3 to 1, that is 3 to 1. And this is 1, 3, because this is fixed 1 to 3, 3 to 1, that is the cycle 1, 3. And this gives the result row 4. Right? This is row 4. So here we write row 4. And we get another result as consider row 3 and row 5. Here row 3 composition row 5. Row 3 composition row 5 is row 3 is 1, 2, 3, 1, 3, 2, and row 5 is 1, 2, 3, 2, 1, 3, and this is composition gives 1 to 2, 2 to 3, that is 1 to 3, 2 to 1, 1 to 1, that is 2 to 1, 3 to 3, 3 to 2, that is 3 to 2, and this gives the result 1, 3, 2. Okay, 1, 3, 2, and this is row 2, and so this is row 2. Here we write row 2. Similarly, if we calculate all the elements in this manner and we fill the composition table as six into 6 element, that is 36 elements, are belongs to this S3. So the composition property hold, and clearly associative also hold, and row 0 from the first row and from the first column. Here the first column and first row becomes the topmost column and left row. So we say that the row 0 is the identity of this set. And we mark, if we mark row 0, here is row 0, here is row 0, here is row 0, this is row 0, this is row 0, and this is row 0. And from this we say that the inverse of row 1 is row 2. This is row 1 and row 2 becomes row 0, and inverse of row 2 is row 1. Obvious, row 1 inverse equal to row 2 and row 2 inverse equal to row 1, and similarly all the inverse we get, and these are from the set S3. So the inverse property is also hold. So this is forms a group, and this group S3 together with the binary composition, usual composition of mapping, is a group, and this is a symmetric group of 3 symbols, and this contains the element 6 element, that is factorial 3. Okay, and it is important to see that about the principal diagonal. This is the principal diagonal. About the principal diagonal, this is not symmetric, because here row 0, but here row 5, here row 4, here row 3, here row 5, here row 4, here row 3. So this is not symmetric about the principal diagonal. So from here we say that, directly say that the group is not commutative or not abelian. So this is a group, must a group, but this is not a commutative group. Okay, so these are 2 important examples with the explanation how can I make a group by a composition table, and this is the today's class. Thank you for watching.